Okay, so I have some sample data for the freezing point depression lab, and I thought I can analyze it for you, so hopefully that will help you with your calculations and should help you with the pre-lab too. So this is the data that I collected. I have the mass of the empty beaker. This is my lowest freezing point temperature of the ice water mix. So before I added the solute, it wasn't quite 0, it was at 0.2. This is the mass of the solute, so this one was about 1, this is 3, almost 5, and then 12.02. And then I watched the freezing point go down, so I added the solute, stir it up, the salt, stir it up, and watch the temperature go down. And the lowest temperature here with the 1 gram was like 1.8 degrees Celsius. This one went down to negative 4.8. -7. So you can see the more solute that you added, the greater the freezing point went down. And then what we did was we strained out the ice and we measure the mass of the beaker in the solution. And that's all the data you have to collect. So you just have to find what 1, 2, 3, 4, 5 numbers there for every one of these trials. And the mass of the beaker is always going to be the same. You only measured the ice water mix one time. So really you only have to measure these things, right? Weigh out your sample, initial temperature or final temperature, and at the end you strain out the ice and you measure the solution in the beaker. So that's all the collected data. Now let's analyze it. Let's just do this first one and see how we do. So the freezing point depression, delta TF, that is just your T final minus T initial. So let's write that down. Delta TF. I'll do things in red. How about that? So my delta TF is my T final minus my T initial, and I'm going to take the absolute value of that. So for that first one, I've got my delta TF is what? My final is negative 1.8 minus 0.2. All right, and that gives me negative 2. And then if I take the absolute value of that, I get 2. So that's my delta TF here. Delta TF for this guy is going to be 2. And you can just type right in there, but I flipped my keyboard around, so I'm just going to write in there. You can definitely type all this stuff up. Now for molality. Oh boy, molality. There's a couple different ways that you can calculate molality, right? We usually my first equation that comes to mind is moles over a kilogram. But I just figured out delta TF. So I can figure out the molality because I know that delta TF is equal to KF times molality. And KF is just a constant. That's the 1.86, right, degree C per molal. And so delta TF over KF will give me molality. So I just divided both sides by KF, which is a constant. So I can find molality this way. Molality is just going to be 2 divided by 1.86. So I find my molality to be 1.075 molal. And I'm keeping extra sig figs here. I really only have 2 sig figs because my temperature is only to 1 decimal place of 2 sig figs there. I'm going to carry some extra ones out throughout this part. All right, so I got my 1 point, I'll put 1.1 in the table because I want 2 sig figs, but I'm going to carry out the rest of these digits while I go through the rest of the calculation. Mass of aqueous solution, mass of the aqueous solution. Okay, so what do I know about what kind of data do I have up here? I have the mass of the beaker plus the aqueous solution, and then I have the mass of the empty beaker. So I'm going to use these 2 pieces of data here to just subtract them, and I should get that, right? So this is the mass of the beaker plus the aqueous solution. So if I subtract out the mass of the empty beaker, I should end up with the solution. So I could just do 65.67. My subtraction's so difficult, 32.81. And when I work that out, I get 32.86. Okay, so that's the mass of the aqueous solution. Now, what is the solution? The solution, right, a solution has 2 parts to it. Solution has the solute, which is the sodium chloride in this case, right? We've got NaCl, and the solute and the solvent here is the water. So I want to find the mass of the water. I know the mass of the solution, right? The solution is 32.86, I think. Yep. And then the mass of my solute over here is 1.07. So I already have that. So that's 1.07 plus whatever the mass of water is, and that's how I can find the mass of the water. So I'm just going to subtract 1.07, subtract 1.07, and I get the mass of water to be 31.79, and that's in grams. So here, 31.79 in grams. And if I want to find it in kilograms, I can just divide that by 1,000. There's 1,000 grams in 1 kilogram, and I get 0.03179. 0.03179. Great. Yep. Okay. Observed moles in my solute. Observed moles in solute. Okay, so how do we find the moles? If I go back to what I remember about molality, molality is moles of solute, right? Solute, that's what I'm looking for, over the kilograms of the solvent. I can figure it out this way. I just figured out kilograms of solvent, right? So this number right here, that's this guy. And I know the molality because I found that up on top. So I'm going to use this and this to help me solve for moles. So if I just multiply the molality times the kilograms, I should end up with the moles. All right. So my molality, and I'm gonna use this molality. I'm gonna not round it. I'm gonna carry out my a few extra sig figs there. I got 1.075, that's my molality, and I just rounded it to put it in the table to represent 2 sig figs. I'm carrying out my guard digits over here. So I've got molality times my kilograms of my solvent, that's this guy, 0.03179, and that gives me my moles, and my moles are 0.0342. Those are my moles. All right, so I got that here, 0.034. Now again, remember I only had 2 sig figs there, so I really only have 2 sig figs in this guy. So those are my moles. Now my observed molar mass, just grams over moles. Great, I measured out those grams way early on, right? Those are my grams, and then I have these new moles down here, so I can just say grams per mole. So I had 1.07 grams and 0.034. And I'm going to carry out this extra guard digit over here. Even though I rounded it in the table, I'm going to carry it out over here because I'm still calculating. End up with 31.29 grams per mole. When I look up the true molar mass, you can either look that up online, or you can calculate it, right? It's sodium chloride. Sodium plus chloride, so that's what sodium is, 22.99, and the chlorine is 35.45. When you add those together, you get 58.44 grams per mole. Great. If we want to calculate the Van Hoff factor, in the lab they told us the Van Hoff factor, that's I, right? I is the true molar mass, so that's that 58, divided by the observed molar mass. So we have 50, so if you just eyeball it, 58 is almost 60, 30 is like half of that. So we would expect the Van Hoff factor to be, around 2, which is the theoretical Van Hoff factor. I'll get to that in a second, but let's just work this one out. 58.44 divided by 31.29, and I calculated that to be like 1.87, 1.87. And then the true, the theoretical Van Hoff factor, we'll think about what sodium chloride looks like here. That's going to dissociate into sodium ions and chloride ions, so that Van Hoff factor, in theory should be about 2. So you can look that up. Great. So that's about how we calculate all of our calculations for this lab.